I have been working on a compiler for a simple imperative programming language called Elna, and last time I fixed a problem with the records. So records are data structures that contain multiple fields, and the most fields has type word. It is just a generic 4-byte type that is everywhere used because we do not have a proper type checker yet. It will be implemented later. And last time I made it possible to use different types besides words as a type of a field. So we now can have enumerations as field type. And I would say that let us try to use more complex types as field types. And the compiler is self-hosted, so we compile the compiler with the previous version of itself, and we will just define a new type and do some tests. So we skip all of the available definitions, and here we define a new type, and we will call it R1, for example. It is a record with two fields. Let it be field 1 and field 2. And we define a record named R2. Let us call it field 3 of type word, field 4 of type R1, and field 5 of type word as well. So, and now we try to compile it. It compiles fine. Then we define a procedure F, at first without any arguments. And we will just return the size of, let us begin with R1. Now we will look into generated assembly for this procedure. And it loads 8 into the register, and this value is returned after that. So x10 is A0. This is RISC-V assembly. The compiler is for RISC-V 32 bits. So this is correct because the record has two fields. Each field is 4 byte. So 8 byte is the correct result. Let us see what happens if we get the size of R2. it returns 12 bytes. And this is not correct, because the actual size should be 16 bytes. 2 4-byte fields, and field 4 is 8 bytes, so we should get 16 bytes. Somewhere I will have a record type expression. It just have a list of fields, but we should also have a type representation somewhere in here, and this is the field representation. And ELNA type record is a representation of a record type in the symbol table, and it has a size field, info type size, and here it is set for the enumeration. That's actually correct. So we can basically, it was ELNA type record, I think. We can actually look for this enumeration value. So somewhere we will have a place where the type is set. So let us look for this record type. And it's here. And what we do here, we multiply the number of fields by 4. And this is actually our problem. And this is name resolution pass. And here we call it recursively. It gets a record representation in the abstract syntax tree, and it returns a type. So the thing that is returned should be actually some type representation with the size. So the type returned will be this ELNA type structure, and it will have a size member. So in here we have field type variable, which is assigned, and member array current has the type ELNA type field type of type word. This is, we can use pointers, I think, already. So we can replace this field type with the proper pointer type. So we can already use pointers here, and we can also replace the type here with the correct type. Let us define a new variable record size of type byte, and we will initialize this variable with 0. And here then we have the field type. We can say that record size is record size plus a field type size. That compiles, and instead of assigning parser node length, we assign the record size to this variable. We can actually just use the result size, but let us see if that works. At least it compiles. And if we look into the assembly again, it is still 12. So do not need this record size variable. We can just set the result size to 0, and then we can add result size plus field type size, and then we can remove this assignment. Or I probably look into wrong assembly. I look into the assembly that is generated by the Bootstrap compiler, but not by the current compiler. Yes, and now we have the correct value here. 16. The next thing that we are interested in, and that, if I remember correctly, is also should be fixed, is field access. And to test the field access, we need other statements than return. we will provide a variable r of type pointer to r2, and we will access a field of this type. We can actually only need a return. We will just return the field value, and if we look at the type once again, let us begin with the field 3. Of course, we do need a variable and not the type. And now we open the correct assembly file this time, that is generated by this compiler stage. It will be stage 18 CL, and here's our f function. This is the epilogue. So we save the argument on the stack, then we load. I think that this is the immediate value that we are interested in, so it just calculates the offset to access the field and saves it in a register. To test it, we just change the, or let us test it with R1 and the second field. Yes, exactly. For example, second field is the second field, so its offset will be 4 bytes. And if I write field 1 here, then it should be 0 again. Yes, it is. So this is the value of x7 is 0. x7, by the way, it is a temporary register. It is T0 or T1 probably, or T2. That can be that T0 is x5. Don't remember exactly, but it doesn't matter. So it will become interesting if we have R2. I actually want to look into the record once again. Stage 18 CL and then R2, and we write that this is the type R2, and we try to access the second field in this record and compile it. Okay. And it has offset 4 bytes. This is actually fine. The interesting case will be the field 5, because it will produce the offset 8 most probably, and this is wrong because the offset for this field should be 12. Yes, so it is wrong by 4 bytes because it calculates the size of each field as 4 bytes, but the size of the second field isn't 4 bytes but 8 bytes. Now we need to find where field access expressions are handled. It will be probably during the 3 address code generation, but this is actually for enumeration values. Field access expression. DC designator. This one looks like what we need. So let us see what happens here. So we set the field offset variable to 0, and then we go through all the fields and we add 4 to this offset for each field. But actually it should be not 4 but the size of the type. Let us look into the field access expression. Field access expression has field and length variables. This is the field name and the length of the field name, and type decoration should be actually the type of the record field. Let us add a variable. We can actually use probably this aggregate type. No, aggregate type is ELNA type record. Expression type. I use it here, for example. Oh, I assign variable. I assign it, but I don't use it. And this is actually the thing. But this is the type of the whole expression. It is actually, it isn't what we need, I think. If I remove it, does it change something? No, it does not. We can just, so we need the type decoration, but we do not need the type decoration of the whole field access expression. What is this current field? So we get this aggregate type. Aggregate is the thing that we have on the left side of the field access expression, and it is actually what we need. And current field is ELNA type field. And this ELNA type field, so it has this this field type. That means current field will have field type member. So let us bring back this expression type and current field length members, and we say that expression type is then aggregate type field type. And that doesn't work. Aggregate type is actually the wrong variable. I think it was current field. Is it? And this is outside of our loop. Actually, what we need is in the loop. I think that it should be assigned here. So the loop, I mean, we do not have proper loops yet. I use labels and go-tos. So these statements that start with a period, these are labels, and I have go-to here with a condition. So it's basically a while loop. I don't see the loops as that important currently, so I will implement them later. And instead of for, we can then add expression type size. And now we go back to the assembly. Build valid stage 18CL. And the offset is 12. Is it correct? So we have one field. The first field is 4 bytes. The second field is 8 bytes. So 4 plus 8 is 12. And the offset for the third field is then 12. So it does look fine. And actually this feature then is finished. I want to rename this expression type variable. We will call it field type. Okay, that's fine as well. So we had this type decoration variable. It is used by a lot of types, and we can set a proper type here. Let us see one time more. How do I use it? I think that I assign a type to it and not a type info. Designator base is type decoration. And aggregate type is ELNA type record. Yes, it is a type and not type info. Type info is used only in symbol tables, and it drops the type structure and adds some additional information to it. So let us look into the type decoration and assign the type pointer to ELNA type. And that fails, of course. Probably because ELNA type isn't defined here. It is probably defined later. We have to move them a bit. I do not think that they have a lot of dependencies, so we just put them in the front of structures that define the abstract syntax tree. We can actually let us try to compile it first. And then we add a comment, abstract syntax tree nodes. Then this one is actually run. Symbol table information, and this type representation we copy it and put it here, I would say. So now we look for the type decoration fields again, and we update other expressions. These are actual expressions, so assignment is an expression. I think so. LNO3 statement. I think I should have a type LNO3 expression and probably LNO3 designator as well. No, I do not have any expression type for the designators. But at least the assignment is an LNO3 expression pointer. Returned is also an LNO3 expression pointer. This next field in the statements, so statements are a list of statements. Yeah, I cannot probably replace this with a pointer yet because it doesn't understand recursive types yet. Yeah, it won't work. So we keep it as is for now. Else, I think else is an expression. Else, and not really kind, this is token type. Elna parser statements. No, it is a list of statements. So it is LNO3 statement pointer. I think at least, so let us look what this Elna parser statements procedure, what it returns. Elna parser statement, and it probably just returns the first statement, yeah. Next, label length. Assignment statement, returned, label declaration, field access expression. Aggregate is also a designator. This is an Elna type pointer. Base, pointer base type. LNO3 pointer type expression. So base is also an expression. And I think that it can be any expression basically. Let us look where it is used. Elna name type expression. This is a different thing. So Elna name type expression, but the base here is an Elna type. Can I just assign it here right away? No, I do not. I do need base before. This is pointer expression and a type expression. This is pointer type expression, array type expression. Yes. So this procedure is called this procedure is called with the base field passed to it. So the type of this LNet node will match the expected type here. So we just write that it is a pointer to the LNet node. And the same is valid for an array that are not supported yet anyway. In the trade, this one is actually an LNOT type expression currently, I think. Well, doesn't matter. Statements, so a list of statements and condition. This is an expression. This is a statement pointer, so LNOT statement. And that's it for expressions, I think. So we have declarations here. Symbol info. This one is an LNOT type as well. Okay, that's it, I think. Let us add a comment to the current stage that we implemented a feature. I'm done with with the work on the compiler itself for today, but a bit earlier I switched the build system to optimize the building the compiler a bit, and I switched from Rake to Ninja, and I already measured the results, and the build is about 2 seconds faster than before, and it is a good thing because we compile very often and every second matters actually, but I still do small adjustments to the build system, and I want to do a little adjustment today too, and so I still use Rake to generate the build description for the Ninja build system. It is then saved in the build directory and called build Ninja. And I want to look into the Rake file, and what I actually do, I generate a rule for each compiler stage, so that the final, you can just see it in the build Ninja file, in the generated file. And basically each stage of the compiler has two rules. For the boot 3 valid, valid 3, boot 3, valid 4, boot 4, valid 5, boot 5, for each compiler stage. But it should be actually possible to reduce the amount of the generated rules by using variables. And we can generate a generic rule and call it bootstrap, for example. And I think that I can use a variable here like bootstrap and then in and out variables. And so this is the rule generation. It isn't interesting, but here so here we have a build statement where we call the compiler. This is probably this one, and no, it generates the compiler itself. What do we build with the compiler? We generate the assembly file. So these are these two statements, this build statement and this build statement. Let us begin with boot. I think that to use a variable, we just need to say that bootstrap is, and then we write the compiler value, and it would be And it would be just this thing here, I think. And then we say that I wanted to do it for the bootstrap first. And then instead of calling this boot rule, we call the bootstrap rule. And look what happens. So I remove then the current build ninja and generate it again. And then I try to call ninja. Okay, it seems to work for the last stages. If I remove the build directory completely, generate the ninja file, and then build the whole compiler. Yes, it seems to work. And now we can remove the unused rules and test it again. So theoretically, the boot rule isn't used anymore. And these valid rules, they can be replaced too. So let us define this bootstrap variable for the validation stage as well, but the compiler will be not in the boot directory, but in the valid directory, and stage number just matches, I think. Yes. So we use, instead of stage number, the previous stage number, and that's it actually, I think. So it would allow us to replace this command with the bootstrap command, and then we can actually just remove this whole block and actually the whole loop as well. So let us test it. We remove the build directory again. We generate the build ninja file. And we try to build, and it looks fine as well. So the first stage of the compiler was written in assembly, and each new stage just adds new features. We have 18 stages currently, and the whole procedure just builds all the stages, and it takes some time. Okay. It can be that I still, so I have these boot1 and valid1 rules. Let us see if I use them. Yes, I do. But I think that we can replace them as well. So this boot1 would be with the bootstrap. This is the wrong statement, of course. So this boot1 would be with the bootstrap compiler build boot stage 1. It is the only usage. And valid1 and valid1 isn't used at all, as it seems. Rule bootstrap to linker rules. C flags. And the final test. So we remove the build directory, generate the Ninja file, and it doesn't work anymore. Okay, that looks fine as well, and this is actually everything that I wanted to do. So just small improvements to the build systems that we will sometimes do, and we actually implemented or corrected the handling of the nested type inside of records, so that the records can contain aggregate types inside it, and the type size and field offset is calculated correctly. Let us open the Ninja file. Yes, it looks shorter, so we just have a few rules, and after that we just have the build statements. That's fine as well, and we will see what we do next time.